Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Cosmic vortices, the physics of accretion disks. Accretion disks are ubiquitous structures in the universe, forming around a variety of astronomical objects such as black holes, neutron stars, white dwarfs, and young stellar objects. These disks are composed of gas, dust, and other material that spirals inward due to gravitational forces, leading to the emission of intense radiation. The study of accretion disks encompasses a range of physical processes, including angular momentum transfer, viscous dissipation, magnetic fields, and radiation transport. Understanding these processes is crucial for deciphering the nature of high-energy phenomena in the universe and the growth of compact objects. At the core of an accretion disk's dynamics is the conservation of angular momentum. As material from the surrounding environment is captured by the gravitational field of a central object, it possesses significant angular momentum, preventing it from falling directly inward. Instead, the material forms a rotating disk, where the centrifugal force balances gravity. However, for the material to accrete onto the central object, it must lose angular momentum. This transfer of angular momentum is facilitated by viscosity within the disk, which acts to transport angular momentum outward, allowing the gas to spiral inward. The source of this viscosity is a critical question in the physics of accretion disks. One of the leading theories is the magnetorotational instability, MRI, which suggests that magnetic fields within the disk can amplify small perturbations, leading to turbulent motions. This turbulence acts like an effective viscosity, enabling the outward transfer of angular momentum. The MRI has been supported by both analytical studies and numerical simulations, providing a robust framework for understanding angular momentum transport in accretion disks. The heating of accretion disks is another fundamental aspect. As the material moves inward, the loss of gravitational potential energy is converted into heat through viscous dissipation. This heating raises the temperature of the disk, causing it to emit radiation across a broad spectrum. The inner regions of the disk, where the gravitational potential is deepest, are the hottest and emit primarily in the X-ray band, while the outer regions emit in optical and infrared wavelengths. The total luminosity of an accretion disk can be a significant fraction of the Eddington luminosity, the maximum luminosity an object can achieve when radiation pressure balances gravitational attraction. Accretion disks around different types of central objects exhibit distinct characteristics. In black hole accretion disks, the inner edge of the disk is determined by the innermost stable circular orbit, ISCO, which depends on the black hole's mass and spin. Within this radius, material plunges directly into the black hole, releasing a tremendous amount of energy. The study of X-ray binaries, where a black hole accretes material from a companion star, has provided valuable insights into the physics of black hole accretion disks. Observations of X-ray spectra and variability have revealed the presence of hot coronae, relativistic jets, and complex absorption features, all of which are influenced by the extreme conditions near the event horizon. Neutron star accretion disks share similarities with black hole disks but also exhibit unique features due to the solid surface of the neutron star. When material from the disk accretes onto the neutron star's surface, it can trigger thermonuclear explosions known as Type 1 X-ray bursts. These bursts provide a direct probe of the accretion process and the neutron star's surface properties. Additionally, the presence of strong magnetic fields in some neutron stars, known as X-ray pulsars, can channel the accreting material onto the magnetic poles, producing pulsating X-ray emission. White dwarf accretion disks are found in cataclysmic variables, where a white dwarf accretes material from a companion star. These systems can exhibit dramatic outbursts, such as dwarf novae, where the accretion rate temporarily increases, leading to a sudden increase in luminosity. The study of these outbursts has revealed the presence of thermal and viscous instabilities in the disk, providing important constraints on the disk's structure and viscosity. Young stellar objects, YSOs, also possess accretion disks, which play a crucial role in the formation and early evolution of stars. These protoplanetary disks are sites of active planet formation, where dust grains can coagulate and grow into planetesimals and eventually planets. The study of YSO disks has been revolutionized by observations from telescopes such as the Atacama Large Millimeter/Submillimeter Array, ALMA, which has provided high-resolution images of disks with intricate substructures, including rings, gaps, and spiral arms. These features are thought to be signatures of ongoing planet formation, revealing the complex interplay between the disk and forming planets. Radiation transport in accretion disks is a key factor in determining their observational properties. The energy generated by viscous dissipation must be transported outward and radiated away. In the inner regions of the disk, where the density is high, radiation is primarily transported by diffusion. In the outer, less dense regions, radiation can escape more directly. The balance between these processes determines the temperature profile of the disk and the resulting spectrum. Theoretical models of accretion disks must account for the radiative transfer to accurately predict their emission characteristics. Accretion disks can also exhibit outflows in the form of winds and jets. These outflows are driven by a combination of thermal, radiative, and magnetic forces. Jets, in particular, are highly collimated streams of material that can travel at relativistic speeds, carrying away angular momentum and energy from the disk. The study of jets has provided insights into the mechanisms of energy extraction from the central object and the role of magnetic fields in launching and collimating these outflows. Observations of jets in systems such as blazars, where the jet is oriented close to our line of sight, have revealed the presence of highly energetic particles and complex structures, including knots and helical twists. The interaction between accretion disks and their environments is another important aspect of their physics. In binary systems, the accretion disk can interact with the companion star through tidal forces, leading to complex dynamical behaviors such as precession and warping. In protoplanetary disks, the interaction with forming planets can create gaps and spiral waves, influencing the disk's evolution and the migration of planets. The interplay between the disk and its surroundings can significantly affect the accretion process and the observational signatures of the system. In conclusion, the physics of accretion disks encompasses a rich and diverse array of processes that are fundamental to our understanding of high-energy astrophysics and the growth of compact objects. From the intricate dynamics of angular momentum transport and viscous dissipation to the complex interactions with jets, winds, and surrounding environments, accretion disks provide a unique window into the most extreme and energetic phenomena in the universe. The study of these disks continues to challenge our theoretical frameworks, motivate new observations, and inspire analogies in other fields of physics. As new technologies and discoveries emerge, the exploration of accretion disks will undoubtedly remain at the forefront of astrophysical research, shedding light on the nature of the universe and the fundamental laws of physics.